All right, morning everybody. So welcome to our third lecture. This is going to be our last lecture where we're going to be talking about particle physics. And before we start on the new stuff, I just want to jump back to what we said was going to be our most important slide for this week, because these are the main kinds of problems we're going to be doing. These are the main kind of things we're going to be trying to understand. Is that we've got this enormous collection of subatomic particles, and we looked at tables of these particles and their properties, and just to confirm, because a couple of people did ask at the end of the last lecture, just to confirm, you do not need to remember any of these details of these particles. You will be given a table of particle properties as part of your formula sheet for the exam, and you'll have access to one of these tables for the tests and whatever. So you don't need to remember the details of any of the particles, or which interactions can and can't occur. What we're really interested in is the sort of underlying structure, is the principle of what the rules are that govern which interactions can occur, which then kind of, tells us the rule for how everything, rules in the end for how everything around us is made. So, this slide is our most important one. It tells us that there are various things that cannot change when we have an interaction between particles, where the particles change. And some of those things are familiar to us. They're things like the electric charge, the energy, including the rest mass energy, the momentum, and then things that we haven't heard of before, like baryon number and lepton numbers. Now, like I say, these are properties that are associated with the particles. We do not need to remember which particles have which numbers. We're going to be given a table that tells us what the properties of each of the particles are. There was then this kind of slight fly in the ointment that just complicates things a little bit, that there are certain interactions that conserve some numbers, or there are some numbers which are conserved in certain interactions, but not all. But we're going to be focusing mostly on the kind of simpler cases anyway. Right, so then we're going to go on today, and we're going to kind of dive a little bit deeper into what gives a lot of the particles, in particular the hadrons, these properties, and it's in the end it turns out to be quite complicated. And again, it's not the details that we need to remember, but maybe just some of the much more general principles. So there were three lepton numbers that I mentioned just there, the electron, the mu, and the tau lepton numbers. And those are then associated with basically three families of leptons. Electrons and electron neutrinos, and each has an antiparticle. Muons and mu neutrinos, again with antiparticles, and tau neutrinos. And those seem to be the only possible leptons that you can get. So there are not that many leptons, and as far as we can tell, there's nothing inside them. We can't break an electron apart and split it into smaller pieces. It seems to be a fundamental particle with no internal structure. Now, it's always a case of watch this space, because they're always designing bigger and bigger experiments, and sometimes we find that things that we thought were fundamental particles are not. But so far as we know, those leptons are all fundamental particles. But there are also things called hadrons. Some of the hadrons are baryons, like protons and neutrons, and some are other things. And it turns out that they do have internal structure. So a proton is not a fundamental particle, but it's made up of some stuff. And the stuff that we think that these are made of are particles called quarks. And we think that there are three families of quarks which come in pairs again, so like up and down, charm and strange and top and bottom, like as shown up in this top right-hand corner. Now, why there would be 3 families of quarks as well as 3 families of leptons is one of those kind of deep questions that we don't really have an answer to. But this is our kind of picture of the so-called standard model of particle physics as it is just now. So if we're saying that hadrons are made up of quarks, then that means that like things like protons and neutrons and everything that what we are familiar with is made of is fundamentally made up of these quarks. And so the question is, how do you make a proton out of quarks? So it turns out that in our standard model, a proton is made of 2 up quarks and a down quark. So we've got these 6 different ones. We've got 2 ups and a down that make a proton. On the other hand, 1 up and 2 downs makes a neutron. And in fact, all baryons are made of 3 quarks in this way. But we can also make particles out of 2 quarks, and those hadrons are called mesons. Again, you don't have to remember, there's all these different names. We don't necessarily have to remember what they all mean. But there's also particular types of hadrons called mesons that are just made of 2 quarks. Now, all we're going to be wanting to do here is, again, use kind of tables to where we're given the properties of those quarks. And the question is how we figure out, we've got to use these tables to figure out how we make up certain hadrons. So the other thing that quarks have is color, which is kind of something that's a bit weird and is a bit like electric charge. It's called a color charge. And once we get to the stage where we can assign things a color, then this gives us really the kind of current standard model of particle physics and quantum chromodynamics, chromo as in color. So each of these quarks, as well as the properties that are listed in this table, also can have a color, red, green, or blue. So you'll notice we've got each of the quarks has a baryon number of 1/3, and the antiquarks all have a baryon number of -1/3. And the charges are also in units of 1/3, either plus or minus 1 or 2/3. And so that shows us how we can, if we add the quarks together, that shows us how we can get something with, for example, a charge of exactly +1e. So then the question is, if we look at this kind of table, can we figure out how a certain particle might be made? Now, we're going to try and do this on a Kahoot question, so let's get our Kahoot started for the day. Able players. Okay. Right, we're going to try and figure out what a sigma plus particle is made up of in terms of quarks, given that it has a strangeness number of -1 and a total charge of 1 unit of the electron charge. So how can you take take 3 quarks from that list and get something with a strangeness number of -1, but a total charge of +1? Should have left more time for that one, looks like. All right, but most of the people who got there got the right answer, which is up, up, strange. So why would it be up, up, strange? Let's go back to our question. We needed to have a strangeness number of -1 and a charge of +1. So if we look at our table, the only one of the quarks that's got a strangeness number of -1 is the strange quark. So we need to use a strange quark. And if we use a strange quark, we can look along the row and we can see that a strange quark has a charge of -1/3. So then we need to get a total charge of +1, which means we're going to have to use 2 quarks with a charge of +2/3, right? If we have +2/3, +2/3 -1/3, that'll get us +1 in total. And we were told in the question that we were only allowed to use ups, downs, and stranges, or their antiparticles, and so the only one of those which has a charge of +2/3 is the up quark. So we're going to need to use 2 up quarks and a strange quark. All right, come back to that in a minute. Okay, so we saw that each quark has a corresponding antiquark, and then I said as well as all of those properties, the quarks also have color, but any given quark can have any of the 3 colors, or indeed anti-colors. So it can be red, green, or blue, or anti-red, anti-green, or anti-blue. And the color charge we can think about a little bit like electric charge, only that that charge can change. Now, we said on the previous slide that a proton is made of up, up, down, and a neutron is made of up, down, down. And we also know that a neutron can decay into a proton, right? Plus some other stuff. That's beta decay. And so this means that if a proton is going to change into a neutron, or vice versa, then one of these quarks has to change from down to up, or up to down. And so how can quarks change from one flavor to another? It turns out that they do this by exchanging virtual particles called gluons. Now, I guess that's, gluon because it turns out that these are effectively the glue that holds the nucleus together. So previously there was this idea of there being a meson that is exchanged for the strong force. Turns out that that is not correct, and our current kind of picture of this is that the strong force is mediated by the exchange of gluons. Gluons are the particle that makes the strong force work, and it's by hadrons exchanging these gluons that they are held together in the nucleus, and when that happens, the quarks change between ups and downs. Right, so here's the kind of picture, roughly, of how this works. The only other thing that we're going to kind of try and understand about these about this quantum chromodynamics is that any particle, any hadron, has to have a total color of like white or no color. And so what that means is that if we have a particle that's made of 3 quarks, those 3 quarks have to be red, green, blue, because that makes white, right, when you add them together. At least if we're thinking about light. Whereas if we have a particle that's made of two quarks, it has to have a green and an anti-green, or a red and an anti-red, or a blue and an anti-blue. And so this means that gluons, if a gluon is getting exchanged between two particles and we're changing what the colors of these particles are, then this kind of process here is constantly happening inside any given neutron or proton, we think. And so a gluon has to have like two color charges, a color and an anti-color, so that, for example, we have this picture where we have a blue, a green, and a red. The blue emits a gluon that has a color of blue, anti-green. The anti-green cancels the green, and then the blue makes this one blue, and finally we're still left with red, green, blue. So this all gets, again, kind of nasty, kind of complicated, and a bit mind-bending. And again, we're not trying to really get into the details of how all this works, but just to get a kind of general picture of these gluons being the particles that hold everything together in the nucleus. Right, so we've got a couple more Kahoot questions. Let's see how we get on with those. Question number 2. Which of the following is true? Mesons are made of one quark and antiquark. Baryons are made of three quarks. Antibaryons are made of three antiquarks, or all of these are true. Yes, all of these are true. So mesons, two quarks, has to be a quark and an antiquark. Baryons, three quarks. All right, we've got another quiz question as well. Quarks can change color by exchanging gluons. In a neutron, up, up, down, a red quark changes into a blue quark by emitting what? How would you change from red to blue? Would you emit a red anti-blue, or a blue anti-red, or a red or a blue to change from red to blue? In my head, I had that down as blue anti-red as well. We've got to get rid of our red charge. We start as red and we want to turn into blue. We've got to get rid of our redness. So we've got to emit a red. And if we want to become blue, we've somehow got to kind of keep everything balanced. And so we've got to emit an anti-blue as well. Right, well done to those who went for triangle. All right. Got one more question coming up a bit later, I think, to decide on the leaderboard positions. Right, so like I said, we had this earlier picture back in the first lecture of the strong force being mediated by these mesons, and that was kind of the picture in the top right was originally how it was thought to happen. But this latest theory, this quantum chromodynamics, is all based on the idea of quarks and the quarks exchanging gluons. And so the kind of picture that we have, this thing in the bottom left is called a Feynman diagram. This is the kind of idea of how neutrons and protons interact. So if we have a bunch of protons and a bunch of neutrons in a nucleus, it turns out that actually which ones are the protons and which ones are the neutrons is constantly changing because they're constantly passing each other these so-called bosons, which are associated with the weak force. They're built out of these gluons, and those interactions are kind of holding everything inside the nucleus. Now, one of the kind of curious things about quarks is that we've never actually seen one. And so they're kind of a theoretical construction. And I guess the idea has stuck around so long because it seems to work. Like using this theory, we seem to be able to predict, and it seems to be consistent with what the experiments say. But what we haven't been able to do is like smash apart a proton and actually see the quarks inside. And the reason that we think that that is the case is due to the properties of this color force, the properties, the way that the quarks are attracted to each other. And they're attracted, again, because they're always passing each other, these gluons. So we think then that this color force has to have some kind of slightly weird properties. And we can maybe kind of think about these properties by drawing some pictures like the ones up the top. So when you have two electric charges, there's supposed to be a negative charge here on the left and a positive charge on the right. When you move them away from each other, these kind of lines that represent the field tend to spread out. And basically the force between the positive and negative charge, the attractive force, gets weaker, gets less as the particles are moved away from each other. And their attractive force gets stronger and stronger as you bring them closer together. Again, if you're not used to thinking about these kind of pictures of electric charges, then you must have at least done the iron filings in a bar magnet experiment in primary school, I guess. And you maybe remember seeing these kind of arc structures. So it's the same when you have a magnet with a north and a south pole. Right, so the electromagnetic force gets weaker as you move the particles away from each other, and so therefore it's possible to kind of separate those positive and negative charges from one another. But we think that the color force is different, so that when we move the quarks farther and farther away from each other, the force doesn't get weaker. And if we think about that in terms of like drawing these lines that represent the force, they sort of wouldn't spread out. And so in order to pull two quarks apart, we have to keep putting in kind of more and more energy to pull them, and it doesn't get easier, it just gets, it's either the same or it even gets harder to pull them further and further apart. We have to put in more and more and more energy. And then at some point there's so much energy, think about these lines as like rubber bands. At some point we've put in so much energy and kind of stretched them so far apart that there's enough energy to create some new particles, some new quarks, kind of within this region where we're pumping the energy in. And so we get something like this picture down at the bottom here, where we've got a charm and an anti-charm. In this case, they're pulled apart from one another. We pull them further and further and further apart to try and be able to see them as individual things. But they get, by the time we put in so much energy, there's so much energy sitting there that we can create some other pair of quarks in the middle. So this was something that we talked about last time, the idea that if we've got enough energy, we can create matter and antimatter. Or if matter and antimatter come together, they release a huge amount of energy, like when you have an antimatter bomb in science fiction films, right? So here we're just creating a new pair of quarks in the middle, and suddenly this C and anti-C that we were trying to actually observe individually, they've now got some partners again, and they're stuck to something else. And this is the kind of thing that you see if you try to kind of take a meson made out of two quarks and kind of split it up. If you put in enough energy, you just get extra stuff coming out. So we had this table. Where's our table? We had this table with these different families of matter, different generations of matter, the three different types of lepton and the three different pairs of quarks. And it turns out that basically everything around us, everything in this room, is made up out of stuff in the first column So protons and neutrons are either two ups and a down or two downs and an up. And we know that there are electrons around us as well. But there's nothing in this room or anywhere nearby which is made up of any of the rest of that, any of the stuff in the middle column or the right-hand column. And I guess the question is, why is that? Why do we only see stuff that's made of up and down quarks and electrons? So that's because basically the other particles are more massive and are unstable. And so when you have stuff that's made of charm and strange and bottom and top and the mu and the tau neutrinos, then it will always decay in some short space of time into something else. And then if that's not made of ups and downs and electrons, then that will eventually decay as well. And at some point we get down to the kind of lowest energy state, if you like. The stable particles are the ones that are made of ups and downs because there's nothing of lower energy to decay into. Now, one example of one of these decays, which doesn't actually involve the higher energy things, the other more exotic things, it only involves the ups and the downs, is this beta decay. So we start with up, down, down. We start with a neutron in beta decay, and we know that the neutron decays into a proton, an electron, and an antineutrino, at least if you did HSC physics and you looked at what beta decay is. And what we now understand is that there's an intermediate step here. So when the down decays into the up, it creates something called a W boson. So that's one of those force-carrying particles. And eventually it's the W boson that then decays into the electron and the electron neutrino. And the W boson is one of these virtual particles. Okay. So that's all. We don't really want to go too much further into that stuff. Like I say, the most important thing that we need to understand this week is really the bits that we talked about yesterday. We're going to be needing to know maybe a little bit about quarks, how we might make a particle out of quarks, but not too much more than that. The quantum chromodynamics is eventually an extremely complicated subject, but it all builds into understanding what stuff is made of, and also in the end, as we'll see next week, what the fate of the universe might be. So when we try and bring everything together that we've understood about all of these particles, then fundamentally we're trying to understand how everything in the universe is structured. Now, we mentioned yesterday that there are four fundamental forces that we're aware of. So those are the strong force, gravity, and the strong force, the weak force, gravity, and the electromagnetic force. Now, the question is, why are there four forces? Why should we have four different forces in the universe? And the kind of holy grail, I guess, or one of the holy grails of particle physics, is to try to kind of basically be able to understand all of these forces as different aspects of a single kind of unifying force. Now, so far, it turns out that we were able to show that the weak nuclear force and the electromagnetic force are actually really the same thing, or that kind of one is a manifestation of another, in the same way that, like, you could think of lots of different forces, like, I don't know, frictional force there's frictional force. Eventually the frictional force is just electromagnetic. It's just the interaction of the charged particles in your hand and the table with one another. So it turns out that the electromagnetic force and the weak force can be unified when we get to high enough energies. So basically, when quarks and leptons, when you can get those close enough to one another, then when we're hoping, or the idea is that somehow the strong force can also be incorporated. So far we think they're different. Electromagnetic is mediated by electrons. The strong force is mediated by gluons. Sorry. Say that again. The electromagnetic force is mediated by photons. Strong force by gluons. But the idea is that if we can get to high enough energies, if we can smash things into one another hard enough and get to high enough energies or temperatures, then we should be able to consider the strong and the weak and the electromagnetic as all parts of the same force. At those energies, it should be possible for quarks and leptons to change into each other. Now, this is all kind of hypothetical, but we have this picture on the right here. So we have either energy, particle energy here, or temperature. You can think of temperature and energy as a bit like the same thing. And now we start to see a little bit why this might be related to the evolution of the universe, because at very, very short times after the Big Bang, the temperature was incredibly high. And so the idea is that immediately after the Big Bang, all of these forces were just the same thing, a so-called grand unified force. And maybe, possibly, if you go back early enough after the Big Bang, maybe gravity is also just some aspect of that grand unified force as well. Now, there are names for these different kind of theories, and these are things that are constantly being searched for. So, a theory that is able to put together the weak and the strong and the electromagnetic forces is called a grand unified theory. And so far, we don't have one. We have managed to unite the weak and the electromagnetic, but so far not the strong. And then if we were somehow able to develop an understanding which allowed us to see gravity as part of that same force as well, that would become something even more impressive than a grand unified theory. That would become a theory of everything. Because, I don't know, these are the kinds of names that physicists come up with. Right, and then the last thing that we want to mention is something about the Higgs particle and the Higgs boson, the Higgs field. So Higgs boson is probably something that you might have heard of, at least in the popular media, because this was something that was discovered relatively recently. So this was proposed all the way back in the 1960s by Higgs, and it was all associated with this electroweak theory, this way to unify the weak and the electromagnetic forces. And the reason that Higgs proposed the existence of this particle, and why we really wanted to find it, was that there was this theory that the electromagnetic and weak forces were really aspects of the same force, but there's a kind of fundamental difference between them in that the electromagnetic force is mediated by a photon which has zero mass. On the other hand, the weak force is mediated by what these W bosons, W and Z bosons, and those are massive. Those have got a non-zero mass. And so how could an electromagnetic force, which is mediated by a massless particle, be equivalent to something that is, but to be equivalent to a force that's mediated by a massive particle? Those seem to be kind of fundamentally different things. So it was proposed that there was this Higgs field, and that the Higgs field was the thing that gave the bosons their mass in a way And to get the full picture, we would obviously need many, many more years of study. But if we try and think about it, just as a simplified analogy, with here like a ball rolling on a curve. So the idea is that the Higgs field is somehow represented by the blue line, and the mass of the particle, the mass of our boson, is represented by the average position of the ball on the curve. So if the energy is high enough, the energy is represented by the vertical position here. If the energy of the ball is high enough, then it will be able to roll from one side of this curve to the other, right? If it's got enough energy, it can make it over this hill in the middle. But if it doesn't have enough energy, it's going to get trapped. So if we now go to the other case, if we imagine that we reduce the energy down far enough, think about potential and kinetic energy here. If the particle doesn't have enough kinetic energy to exchange for potential energy to get to the top of that hill, then it's never going to get out of this valley, and it's going to roll about on one side, and it's going to have a non-zero average position. So again, if the energy is high enough, the position of that ball will, on average, be in the middle, because it'll be able to roll from left to right, and if you follow it far enough, it'll spend an equal amount of time on the left and the right, so it'll have zero energy. Whereas if we reduce the energy low enough, then our ball will be trapped on one side and we'll have a non-zero average position. So the idea was then that at high enough energies, the bosons, those W and Z bosons that mediate the weak force, will have zero mass. And so therefore we can imagine that it's consistent with the electromagnetic field, which also is mediated by a zero mass particle. But when we reduce the energy low enough, that's when the electromagnetic and weak forces somehow become separated, because those W and Z bosons for the weak force become massive. So because the grand unified theory is this holy grail, and because the first step is to unify the electromagnetic and weak forces, that's why there was so much, I guess, anticipation to try to actually find this Higgs boson, because if we could find the Higgs boson, it would show us that there really was a Higgs field, and it would show us that this picture, this explanation of how the electromagnetic and the weak forces are kind of basically the same, that would be correct. Right, so that's why people were so excited to find the Higgs boson, and it was looked for many, many years. It was proposed in the 1960s, and finally, in 2012, first in CERN, and then in some other kind of confirmation discoveries in subsequent years, the Higgs boson was finally observed, and its mass was measured. It's an extremely massive particle, thousand times the kind of mass of some of the particles we were looking at in our examples yesterday. Right, so today we're going to finish up with a Kahoot question. Today was kind of a bit of a trip down Alice's rabbit hole or something like that, right? Like I say, we're not expecting to understand the details. This is very broad brushstrokes just from today. The main thing that we're taking from this week is this idea of being able to understand particle interactions with the fact that their properties have to be conserved. But hopefully we've taken a small tour and seen some of the weird and wonderful aspects of quantum chromodynamics today. And then next week we're going to move on to lots of pretty pictures of the universe and trying to eventually see maybe where some of this stuff comes into our understanding of the Big Bang and where the universe might be going. But we'll finish up with a Kahoot question. Whoops. Right. Here we go. One more Kahoot question. So, grand unified theory. What is a grand unified theory? Does it unite the electromagnetic and weak forces? Does it unite all the forces? Does it unite the strong and weak forces? Or does it not include gravity, but all the other three? Does not include gravity. Something that unites all four fundamental forces is a theory of everything, but a grand unified theory is just weak, strong, and electromagnetic. Let's see what that's done to the final positions on the podium. All right. Congratulations to our podium sitters and our runners up there. And yeah, we'll pick things up with more lectures next week. Of course, next week the tutorials also start. There will be a tutorial for the problem sheet on particle physics, and the labs start up as well. Before the labs, again, make sure you look at the stuff that's on Canvas. You have to have done the online safety induction before you come to the lab. If you come to the lab and you haven't done the online safety induction, then you will be asked to go away and do the online safety induction and come back. When you come to the lab, you don't need a lab coat or glasses or protective equipment, but you cannot wear thongs on your feet. You've got to have covered footwear. That's about all that you need to remember. And please do try and get a printout of the lab manual, although I've heard that the print shop is a bit backed up. So if you haven't placed an order, then I would try and do that ASAP, because they always have a lot of printing to do at this time of semester. So there's a link on there on Canvas for you to go on and order a copy from UON Print. Right, otherwise that's us. Happy to answer any questions now that anyone has.
Excuse me, sir.